Recording is rolling. It's Tuesday, March 4th. So, reminder SAT, of course, coming. Oh, God. SAT coming up in 2 days. So, remind you guys where I posted all this information. So, I posted some things this week. We got volunteer hours here. We got updated posters here. Here's your two SAT files. This file here shows where you're testing if you're testing, which is most of you guys. Most of you guys are taking the SAT in 2 days, and this will tell you where to go. This other file tells relocations. Some of you guys are not taking the SAT. It's going to be relocations, including for this class because there's testing in this class. So there's going to be no physics for the first 4 classes on that. All right. And then, of course, here's yesterday's videos. Okay, so we got it there. All right. So all that is right there. Okay, so speaking of relocations, here's my own relocations for my first 4 classes. So on Thursday, in 2 days, you're either taking the SAT or first 4 classes you're relocating. Okay, you guys got that? All right, and all that information is on Google Classroom. All right, so let me give you guys a quick recap of yesterday, and then we'll get into what's going on today. You guys that you're gonna have a prism and a laser, so that's fun. We're gonna do that about last half of class. So first, recap of yesterday. Yesterday we were talking about reflection. So if you have a mirror surface, like a reflective surface, the law of reflection very simply says that relative to this normal line, and you guys are gonna be drawing some normal lines today. Guys, what does normal mean? Perpendicular. So you guys see this line is perpendicular to this mirrored surface, right? You guys gonna be drawing some normal lines today, okay? Relative to that normal line at this angle of incidence, this angle of reflection has to match that. That's all reflection says. Okay? Now for a plane mirror, that would be true. And then what about for a curving mirror? So here I have a convex mirror, like a big mirror ball. Okay? So the rule is, well, if you aim a laser light straight at the center, it's gonna reflect straight back. But if you shine parallel to that, it's gonna reflect off in such a way that this reflected ray could align with this focal point, which is halfway to the center. Okay? And so we've got this focal length defined as half the radial size. Whatever the radial size is, half of that, here's your focal distance. Okay? And you can use that too. We made a bunch of ray diagrams yesterday. Now here's for a plane mirror. Here's for a convex mirror. Object, image, the image being the reflection, where's the reflection show up? And then we checked the ray diagrams against this equation. 1 over the focal length is 1 over distance object plus 1 over distance image. We did a few equations yesterday, and everything was pretty well lining up. Plus or minus about half a centimeter. Okay, so tell you distance object, distance image, focal length there. Guys, what was the focal length again for a plane mirror? What was the focal length? Another way to say that is for this mirror ball to appear approximately flat on the surface, it would have to be how big? How about really, really, really big? How about like infinity big? Right? Right? And half of infinity is still infinity. So yesterday, when we ran the equation, this equation, for a plane mirror, we plugged in infinity for F. And guys, what was 1 over infinity again?
0.
0. Yeah, 0. Right. Hence, if this is 0, distance object and distance image are going to be, well, just negative of each other. Right, same value. Right. Then we switched over and started doing concave mirrors. Now, one example of concave mirror could be this cosmetic mirror. That's like this this top picture right here. If you have your face really close to the mirror. And another example was, well, is that flying saucer going around somewhere out there? Oh yeah, it's over there. You guys can pull that apart. It's a couple of parabolic mirrors, which is creating a real image. You guys remember a real image? It looks like it's hovering in front of the mirror. Right, you guys remember that? This equation still applies to those also. Okay, so you guys got those. Okay. All right, now we're ready to switch over and do something new, which is refraction. Refraction. So what have I got for refraction? You guys ever put a straw in a glass of water and it looks like it's all bent? Okay, it's not really bent. It's just huh?
Once before.
Yeah, once. Yeah, did that once. Yeah. So
I'm not gonna lie, yeah, I've done it. Yeah, once or twice. Maybe.
Once or twice.
I'm not gonna be like, no, I haven't. Yeah, everyone's done.
So why? Why? Well, let's find out why.
Inclined plane. And I got some wheels. And I'm just going to roll the wheels down the inclined plane. All right. What I'm going to do is I'm going to roll the wheels from a nice smooth sidewalk onto a rough piece of material. It's almost like wheels rolling along a sidewalk into the grass, or light coming down and interacting with the material and slowing down. If I roll them at an angle, did you see it bend? It came down like this and then bent. Let me put that on the board. My wheels are coming down in this direction, and they're coming from the smooth surface to the rough surface. When the wheels get to the rough surface, what happens to the speed of the wheels? Slow down. You know why they slow down? Because there's an interaction with the wheel and the material. Let's suppose it's like the little pieces of cloth on the towel, or maybe it's like blades of grass on a lawn, okay? There'd be some interaction, so this part would slow down. But what happens to this other part over here? It continues going quickly. So what happens? It sort of kilters. And so what happens is it goes like this. When both wheels get in there, they're going the same speed and they continue at a straight line. So there's no mystery as to why the wheels will kind of bend over, is there? I mean, if you can move along like that and something's on the way, won't your hand go like this? I mean, part of it's slow. Well, guess what behaves the same way? Light waves. When waves of light come from above, it's a hit water. Maybe the waves of light are coming from the sun. Like that. And we got a ray coming down like that. Incidentally, it turns out a light ray and the wave fronts that represents, these are like the crests of waves. Think of water waves, yeah? Right angle here again. Always a right angle. See, even the axis of a wheel and the direction of which it's traveling, right angle. Okay? So what happens over here? These waves of light come down, and when they hit the water, what happens to the speed of the waves? Oh, you don't know that. Well, check your neighbor. They somehow go faster. What's the answer again? They slow down. Okay, the waves slow down. So what happens? They bend, and they sort of bend like this, and they get closer together. So the wavelength gets a little less in here, but the frequency of the wave stays the same.
Frequency stays the same. All right, so how does that lead to this? So I'm going to lead up to this, but I've got his model copied right here. All right, so do you guys remember this wave equation? You guys remember this? Guys, what does this say? Can you guys read this? What does it say? What equals what times what? Speed equals wavelength times frequency. You guys remember that? Speed equals wavelength times frequency. Okay. Now, light's a type of wave. Right? So it's supposed to got this ray of light right here. Like, like it looks kind of like a laser light, doesn't it? Right? You guys got some lasers. Right? So got a little laser light right there. Right? Now, when it hits this water, it's going to slow down, and that's going to kick off this process that makes it bend, and that bending is called refraction. Okay. So why does it bend, and how much? Okay? So, see, if it slows down, now you're messing with this equation. If you're decreasing the left side of the equation, overall you have to decrease the right side of the equation. Okay? You guys see how the light's going from the air into the water? Okay? Remember, light being a wave, maybe it has like crest. There's some distance from crest to crest that's called wavelength. Okay. Now, if it slows down, that means per unit time it's not moving as far. Say if these crests get closer together. Right. So if the wavelength's decreasing, that would correspond to the speed decreasing. Right. In fact, it's exactly proportional. If it's like half the speed, it'd be half the wavelength. Okay? Because the frequency has to stay the same. And you can see that here too. Guys, isn't it true that the frequency of these crests leaving the air has to exactly match the frequency of the crests entering the water? Right? Bleep, bleep, bleep. Here, bleep, bleep, bleep. It's the same frequency. Okay? Now, there's other ways to explain this too. That's the way I think of it. I've seen other a little bit different explanations on this, right? But yeah, ultimately, the speed goes down, so the wavelength goes down, so it bends, it refracts. Right? You guys that? Now, how much does it refract? And that you can get from Snell's law. Now, to understand Snell's law, you got to know what this N is. This N is called index of refraction. Okay. And guys, what does C stand for in physics? The speed of what? Speed of light. You guys, speed of light. You guys know C is the speed of light. Okay. V could be the speed of light inside the material, like in this case, inside water, or if you have a prism on your desk, inside the glass, right? Right. It's going to be a little bit different. Oh, you can see some refraction. Look at that. You guys see some refraction right there? Right. Just look it through. So it's all bendy. Right. I bet you can calculate the index of refraction of this. Actually, that's exactly what I'm having you guys going later today. It's going to be your lab today. Okay. So this index of refraction is a ratio. Refraction, right? Is a ratio of the speed of light in a vacuum compared to the speed of light inside the material, which is slower. Okay? So here, guys, what makes sense before I start popping numbers in? Oh, is this index of refraction? What sounds more reasonable? Could this be 0.8 or 1.2? What sounds more reasonable? Because one of those is impossible, and one of those would be realistic. 0.8 or 1.2. What could this be? Huh. 1.2. How do you know it has to be a 1 point? Well, it has to be more than 1. How do you know this index has to be more than 1? Yeah, speed of light is fastest in a vacuum, and that's what this number is right here. So we're going to take this to be 3.0 times 10 to the 8 meters per second. That's the speed of light in a vacuum. It actually is like 29979 something, but I just rounded to that. Right? And it's going to be slower inside the material. Now, different materials, it's going to be different, like glass, different from water. Actually, the different kinds of glass, and then water is its own thing. Maybe like olive oil could be its own thing, something like that. Okay. The index of refraction for water, I'll put in water. I'll tell you guys is I'm going to call it 1.33, which is different from the glass on your desk. You guys are going to figure out the glass on your desk later. Okay. But let's play around with this a little bit. I wonder what, say, like these angles could be or whatnot, right? Let's say we're figuring this out from scratch. Let's say you do this experimentally. So I put the pencil in the water and I look at it from above and say, oh, look, all the pencil got all bent. Oh, no, but it's not really, right? The pencil's fine. But from my eyeball here, it looks like it's bent, right? And what if I take the protractor and I measure some angles? I think, well, let's see. Now, guys, again, you're measuring the angle with respect to a what line? No. Normal line. You can see the surface of the water here, and then this dash line is perpendicular to that. So let's say I measure I'm just gonna make up some numbers, but let's make believe. Oh, actually, I was gonna use 40 degrees anyway. That is 40 degrees. Yes, that's 40 degrees. Right. Actually, what is this angle here exactly on my poster? I need to. Okay, yeah, that's not really accurate for water, but let's make believe that this one's 29 degrees. Is that okay? All right, make believe this is 29 degrees down here. Right. So if that's true, then here's Snell's law. Snell's law goes n1 times sine theta 1 equals n2 times sine theta 2. Okay. Now, on the side of air, actually, let's start with the vacuum. Because if you have a perfect vacuum, I'm looking at this right here, a perfect vacuum, what would n be for a perfect vacuum? And space.
Oh, 0. No. 1 over infinity.
Well, what's the speed of light in a vacuum? Is it just c? Yeah, it is itself. What is c over c? 1, exactly. Isn't that 1.0? Right? Now through air, it's really close to that. It's like 1.00 something. I think it's like, okay. So I'm just going to round it to 1. I'm going to say on the side of the air, I'm just going to call this 1. Okay. And you guys can do the same thing later today. So you guys know your lab later today, you're going to call index of refraction of air just 1. Right? Okay. And then sine of, I was calling this 40 degrees right here, equals, let's say I want to know what is index of refraction of water. And I get the refracted angle is 29 degrees. Okay. All right, is that okay? Good. Okay. Who can solve for the index of refraction of water? Can you guys do that? You guys have calculators? Somebody tell me, what is the index of refraction of water with those numbers? That incident ray and that refracted ray? You can tell me, what's the index of refraction of water? Can everybody solve? I think everybody should be able to solve that.
Easy peasy. Hold on.
Yeah. Who knows how to math?
1.32.
Ah, got it. So just take the sine of 29 degrees, divide it over. Okay, so it's like this. 1 times sine of 40 degrees, divided by sine of 29 degrees. I put this here, you guys can see it. Yeah, it's like 1.3 something, right? So I think the textbook value actually is like 1.33, which is rounds to anyway. Okay, those angles. So that's the index of refraction of water. That tells you, remember what that tells you? That tells you the ratio that light will slow down in water compared to a vacuum or compared to air. Okay? how about this? What if you change this beam angle and you get it flush with the surface and it's going to approach some limiting value as it refractions to the water? Or from the other side, if you're a fish swimming around the water and there's a bunch of light rays leaving you. Here, actually, I got one of these lined up here. Here's the one I'm picking up. I'm trying to introduce another idea here called critical angle. You guys see this? You guys see that this fish might be sending off lots of light rays in all different directions? Right? Okay, and the ones that go straight up, okay, they go, ones that go some angle, okay, they're gonna refract out some angle, okay. But there's some critical angle here. You guys gonna figure this out later for the glass piece, where the angle of refraction is 90 degrees when it goes back into the air. You see that? Right. And anything beyond that, is there any more refraction? No. No, was the answer. It's all reflection, and that's called total internal reflection, where there's no more refraction. Okay. Let's show you guys that in motion. Okay. So I got a couple of Snell's law here. Snell's law. Okay. So he's got this prism piece. Now I got two different kinds of prisms floating around. Some of you guys have this semicircle looking glass piece. Some of you guys have a triangle piece, like I have a triangle piece. So I'll show you guys an example in a few minutes. So whichever one you use. Now, if you do use the semicircle piece, notice throughout this video, he's aiming that light straight at the center. So he's aiming straight at the center. And there's a reason he's doing that. Because I see a refraction here. See, the light goes from the air to the glass. It bends a little bit, it refracts. But as long as you're aiming straight at the center, then when that light emerges on the curved side, it's always going to be perpendicular to that curved side because it's a part of a circle. So it doesn't actually bend again. And therefore, you can read the angle straight off here. You guys see that? So it only kind of refracts once. Versus later on, when I demo with you guys the triangle piece, or if you have a triangle piece, keep in mind it's going to refract twice. It has to go from the air to the glass and then from the glass back to the air. Okay. But here, it doesn't actually bend a second time. Okay. Also, guys, notice all these angles are with respect to this. What line is this called again? Normal line. That's what we're measuring the angles with respect to. This is normal to this glass air surface, perpendicular to that. That's what normal is. Okay? So right at this moment, here, let's grab these numbers because I just paused it at a random point. You guys see this is about 50 degrees. This is about, I don't know, maybe 31 degrees. You guys see 50 versus 31? Right? Could you figure out the index of refraction from just that screenshot right there?
No. Yes.
Yeah. Let's figure it out. So we're looking at, here, I'll kind of sketch this out real fast. Right. We got this going on. Right. He was shining in the laser light this way, and it refracted out that way. So this was 50 degrees, and this was 31 degrees. True? See that? So let's go N1 sine theta 1 equals N2 sine theta 2. Okay? Is everybody paying attention here? Because you guys know you're going to do this in a few minutes, right? Okay. So on the side of the air, what is the index of refraction of air again? Pretty close to 1. It's like 1.00 something. So call it 1. Okay. And what's the angle that matches that? 50 degrees. Okay. Now we don't know the end of the glass, but we do know the refracted angle, which is this one right here, 31 degrees. Can you guys solve for the end of the glass? I'll do it. You guys do it. Let's see if we get the same thing. The sine 31. Okay. Yeah, that's what they've been getting so far today. 1.49. You guys think it's supposed to be like 1.5 basically? Probably about 1.5. Okay, do that. Now, back to this video though. Okay. If you keep going, get close to the end of this. You guys see how this incident angle is approaching 90 degrees? Like at some point, maybe you could go like 89 degrees. That's about it. And then this refracted angle is going to approach some limiting value. Could this refracted angle ever reach like 50 degrees? Probably not. Just looking at it right there. Yeah, it's kind of running out. In fact, it looks like the reflection is getting stronger and stronger, and that refraction is really weak. It looks like it's petering out about 42 degrees or so. Do you guys see that? Right. Guess what that, I'll call it 42 degrees. Guess what that 42 degrees is called? It's called the wet angle. Critical angle. Right? And you can also see this from the other side. Suppose he's shown in the light from the curved side. He's about to do that on this one. Right? Trying it in the curve. Oh, look, it's like the same thing but backwards. You can see, all right there. Bam. It was right there. Oh, look, it's the same angle. It's about 42 degrees. You guys see 42 degrees right there? Right? Where it stopped refracting and now it's all total internal reflection. And anything beyond 42 degrees, it's only going to reflect and it's not going to refract. Okay, is it? Okay. So there's two ways you can find the critical angle. There's two ways. One way is you could find it empirically, right? You do exactly what you just saw him do. Just change the laser angle until it no longer refracts, it only reflects. That would be the critical angle, right? With respect to this normal line. The other way is you can calculate it if you already know the index of refraction. Okay. Okay. Let's see, because you guys saw it was about 42 degrees. Let's see how close that would be with the calculation method. So I'm going to set up another Snell's law. N1 sine theta 1 equals N2 sine theta 2. Whoops, N2 sine theta 2. It's an N right there. Sine theta 2. Right. On the side of the air, I'll call this 1, and I'll call this sine of 90 degrees, because 90 degrees would correspond to that scenario where it's going critical. So can I find the critical? Oh, whoops. Sorry, that's not what I'm looking for. I meant to call this 1.5. Let's set this up again. 1 times sine of 90 degrees equals, we're calling this 1.5 for the glass, or if you want water, you put in 1.33, but yeah. Okay. Sine of, okay, and we're going to solve for the critical angle. So we're doing this mathematically rather than empirically. Remember, empirical is you actually shine the laser and just see what happens. Mathematically is we're going to apply Snell's law, and we'll get this with the calculator. Okay. Can you guys solve that? Can you guys solve that? Okay. Like, here, give you guys a hint. What is sine of 90 degrees? 1. It's 1. Okay. Like, I like to think about unit circle. If this is 0 degrees and you go around counterclockwise, here's 90 degrees, and sine on a circle tells you how high you are in a unit circle, which is 1. So this whole thing right here is 1. Getting divided over 1.5. And then how do you extract an angle out of a sine? You have to take a what?
Inverse sine.
Inverse sine. So I'm going to do inverse sine of, okay, this is all 1 over here, divided by 1.5. I'm getting critical angle is, oh, look what it is. It's 42 degrees. Exactly. Like you guys saw in the video, empirically, it was also 42 degrees, wasn't it? Ah, look at that. So there's 2 different ways to get the critical angle. You guys got that? Okay, are we good? All right. All right, so, yeah. I think we're ready for this lab time. All right, so guys, get a paper somewhere. If you don't have any paper, of course, I always got paper on these stools in the middle of the room. Write your name on the paper. You'll have the rest of the class do this. I'll do a demo with you guys here, and I'll give you guys the rest of the class. And if you finish this before the end of class, which I think you'll be able to, then you can turn to the lab. Right. So I'll call it Snell's Law Lab. Snell's Law Lab. Okay. So 1 page of paper per student. I want everybody to do this. Now I've only got so many lasers and so many prisms, so you're gonna have to share these materials around. Right, but I want every student to do this individually. So trace out whatever prism you have. Again, I have a triangle prism up here. You might also have a triangle prism, or you might have a semicircle. Okay, but I got that traced out. Then this laser light. Now guys, are you guys gonna shine the laser light in each other's faces? The answer to that is definitely no. Definitely no. You're not gonna do that. Because that could cause permanent damage to your friends. And they will remember when they're 50 years old. I've never been able to see out of my left eye since I was 17. So yeah, keep the laser out of each other's faces. But notice how here, if I shine it at some angle, you guys see this bead of light emerging on the other side over here? Right, so I can trace a path. So see, I see I'm shining in the laser at this here. Actually, I should switch to pink ink. Here, I'll do pink ink for my laser light. It's entering that way and it's exiting right there. You guys see that? In that way, out that way. You guys see that? Okay. Now there's some other stuff going on too. I see some reflection here. I see some internal reflection out there, but I don't care about it so much. I just care about this refraction. You guys see that? Okay. So let's get a full path. So I was shining in the laser at this angle. Bam. It was exiting this way. Bam. And in the middle, it must have been doing this inside the glass. So there's actually a double refraction from the air to the glass and from the glass back out to the air. You see that? Okay. So I've actually got 2 sets of data to work with if I wanted. Okay. Now I need to measure some angles with respect to a normal line. So I got to get a normal line. So take my protractor. Here, I'll do this the point where the laser light entered the glass. Okay. zero out that side, go to 90 degrees, bam, and then draw a normal line there. Okay. So here's my normal line. Okay. Then here I'm going to go ahead and extend this laser light, extrapolate it, say, well, it was headed this way while it was inside the glass anyway. Okay. So now I got a couple of angles. Here is my angle on the side of the air. I'll call it theta A for angle for air. Okay. And here's the angle on the side of the glass. Call it theta G for theta glass. You guys get it? Okay. A couple of angles. Okay. Okay. Now, take a protractor and measure what these angles are. Right. So this angle is, well, take it, but I don't want to give away too much because I want you to do this yourselves, but I could measure the size of this angle, how many degrees, and same thing with this refracted angle. I could also measure that, how many degrees. You guys that? Okay, you guys that? Okay. Now, what's the goal of this lab? I want you guys to find two things. So question number one is, what is the index of refraction of the glass? All right, that's question number one. Okay. Now, you guys just told me a few minutes ago, because what sounds more reasonable for index of refraction? So I'll say n equals something. Could it be 0.8 or 1.2? What sounds more reasonable? Yeah, it's got to be more than one. Right? It's got to be. So I'll narrow it down. It's between 1 and 2. So it could be 1.2, 1.4, 1.6, 1.8, something like that. Yeah. Okay, yeah, where's this dash line come from? This is a normal line. Normal line. Normal meaning, of course, perpendicular. Perpendicular to the surface. So what I did was I zeroed out this surface where the laser light is going from the air into the glass. Okay. Zero that out. I'm going to put this node right here on this point. Bam! Right where that transition is happening. I'm going to zero out this face and then go to 90 degrees and put a point right there. Bam! At 90 degrees. Then I connect that back to that original point with a dashed line. Right? And that line is perpendicular to that surface. Right? And I'm measuring all the angles with respect to that line. Okay? Well, I should say both of these angles, right, to be grammatically correct, because there's only two of them, right? This angle and this angle. Okay? Two angles. Okay. So what is the index of refraction of the glass? And I'll tell you guys it's something between 1 and 2. And it might be different for different groups, because some of you guys might have this little triangle. I think this triangle is some kind of plastic. And some of you guys have that semicircle piece, which I think is definitely a different material. It's like a heavier glass type. So there might be different answers just in there. And the other question I want you guys to tackle is, what is the critical angle? Critical angle. Right. So I did a few examples with you guys. So if you've been keeping notes today, then you can remember there's two ways you can find this. So so you guys know you can use Snell's law to figure out index of refraction. You can calculate it. Here, I'll probably leave this poster up while you guys are doing the lab. Okay. Okay. And then for critical angle, there's two ways you can find critical angle. You can find it empirically by just changing the angle of the laser. Actually, on the side of the air, you have to change it all the way to like 89.9 degrees, which is kind of tricky to work with, right? Or this might actually be easier, is once you know the index of refraction of the glass, you can calculate the critical angle using Snell's law, which we just did like 5 minutes ago in the notes. Okay? Right. So once you got both of those answers, you can turn this into the grade tray. I will walk around and help you guys out. I think you'll probably finish this in class today. Right? If you don't, then at least get all your data so you can turn it in tomorrow if you have to do the calculations at home. Right, and that's a wrap on the recording.